Okay. Hello, everyone, and welcome to another meeting of our reading group. Today, I'm excited to have another great speaker, Herman Kamper from Stellenbosch University. And as always, if you have any questions, feel free to raise your hand or drop the question in the chat, and we go over them during some pauses in the talk. I think without any further ado, the stage is all yours.
Thanks so much. Thanks a ton for having me. I think I also mentioned this beforehand, but there's been some really awesome speakers in your series. So I'm like really happy to be on your website with my name next to some of my role models in the field. So thanks a ton for having me. Also, I'm going to talk about voice conversion and the geometry of self-supervised speech representations. Before that, I thought I would just quickly tell you where I am. So I'm at a university called Stellenbosch University. Stellenbosch is a very small town. It's close to Cape Town. So if you imagine the globe, it's like the southernmost tip of Africa, just like 45 minutes inland. This is a picture of the town. So the town actually just has, I think, three things. It has a university. It has wine farms, basically surrounding the farm, the town, and then it has awesome mountains. So all the red-roofed things, those are Stellenbosch University. I'm actually sitting in this ugly yellow building at the bottom of the screen right now. So I wanted to turn my camera out, but this is more or less the view from my office. Not exactly, but almost. I took this from during COVID on one of the walks. Awesome place if you ever want to come and visit. It's a great place to do research, but also a great place to do walks and go for wine tours. So come and visit Stellenbosch University. Awesome. Yeah, so I'm going to talk about self-supervised speech representations and specifically how that fits in with voice conversion. And I'll spin a little story about this. So I think all of you know that we basically live in the age of language models. And so text-based language models, everyone knows about it now. My dad told me about reading it in an Afrikaans newspaper, and then I knew, okay, language models are all over the world. Mainly text-based models, but you guys know that speech and have also been affected by this. And so we have spoken language models, things like Hubert and WAV-LM, or contrastive predictive coding. And these are models that operate directly on speech. So for example, Hubert, some latent representations are masked, and then you try and predict basically quantized versions of the input as on the output side of the model. Contrastive predictive coding is kind of an older approach, which tries to discriminate latent representations that is going to follow in the sequence from those that doesn't follow. And it turns out that these models, if you train them well, they learn really, really good features from language. So for instance, you can train a model like Hubert. It's trained without any label data, right? So you just train it with this masking task. And then it turns out that could be a really good initialization, for example, for speech recognition. So you can then fine-tune the model subsequently. I am really interested in zero-resource speech processing. So these are models that learn just from raw audio without any labeled data. And in our group, we found that models like Hubert just provides really good speech features for downstream applications, for example, for discovering word units, or for segmenting and clustering speech. So that our little subfield have also been taken over by this. And what I'm going to talk about in this talk is actually how we can use something like voice conversion to see a little bit on what happens inside these models. What happens in these self-supervised representations, in the SSL features inside these models. And that's what I'm going to talk about. There's a big caveat, basically the lie for the talk. I'm going to say, oh, we look at SSL features or self-supervised features, and I will make it sound like it's any self-supervised features, but actually what I mean when I say that is specifically we have LM layer 6. Okay, so we're actually just looking at this one layer. It turns out it works really well for the task of voice conversion. Hopefully what I will describe while I'm lying will also translate to other self-supervised features. So we'll look at these 1 or 2 4-dimensional features. Okay, and I'm just going to summarize the whole talk for today. What I'm going to do is I'm going to first introduce 2 very, very simple voice conversion approaches. They are super simple. They're a little bit dumb, but despite that, they give pretty good voice conversion results. So after introducing these two approaches, what I will then do is I will try and explain to you how these two approaches allow us to see what SSL features are actually doing and what the geometry of the SSL feature space looks like. The two things I want you to take away from the talk at the end is that simple models are cool. Really simple approaches are pretty cool. And then the other one is that I think voice conversion is a really nice way of actually probing what happens inside these SSL models. So people have probed these models in different ways, normally by training a linear classifier on top of some latent representations and asking, can I discriminate the speaker, or can I classify the phone that occurs in this specific frame? And that's a very useful approach. These straightforward linear classifiers, they have shortcomings as well. And what I will present here is kind of an alternative to that, or maybe a complementary approach using voice conversion. So the first simple method that I will talk about is a method called KNNVC. It stands for K-nearest neighbors voice conversion. And this is work that I did with two of my PhD students, Benjamin or Benji and Matthew. It's a little bit older, so it was at Interspeech 2023, but people still use this approach. So I should maybe just introduce what voice conversion is. So how voice conversion works is the aim of the game basically is that you have some input speech that you want to, that the speaker said, a little utterance. And then what you want to do is you want to have this same utterance as the output of the system, but spoken by a different speaker. Okay, so it should sound like this. It should have the same content, but it should be a different speaker. And normally how this works is, let me make this concrete. So Herman, will say the middle classes, and then we want it to sound like Pune. Okay, and as conditioning to this model, we'll give it some reference speech, some other examples that Pune has said before. Okay, and then we want the model to convert. Normally, most of the systems, you can kind of condense it down to some form of feature extraction. And then in the feature space, you do voice conversion. And then you have a vocoder that goes from those latent representations back out to the speech in the target speaker's voice. So I'll actually start by just playing you examples from KNNVC. So I'll just play this in sequence. I'll play you the input to the system. Then I will play you the target speaker. We want it to sound like this speaker, and then I will play you the output. So the input is this.
A narrow channel formed a passage through the ridge of rocks that protected it from the open sea, and which, even in the roughest way,
somehow,
we want it to sound like this.
Feeling was the strongest. This day it seemed as if she could bear it no longer. A narrow channel formed a passage through the ridge of rocks that protected it.
Okay, you'll see I click quickly because I'm on a Mac, and for some reason my Mac can't allow me to pause. So I'll just cycle through sometimes, and I hope that's fine. But you get the idea. And this is actually output from KNNVC. I'll just play the input quickly again, and then the output again. So the input is
a narrow channel formed.
The output is
a narrow channel formed a passage through the ridge of.
Okay, and that's with KNNVC. Okay, so how does KNNVC work? It works like this. So you have some. I'll just quickly run through it, and I see there's a question. Then you can stop me. So how KNNVC works is you have the source utterance. So this is something about the passage of the ridge of rocks or something like that. So this is the thing that you want to keep the content from in your input speaker. And then this is me speaking. This is Pune's speech, some example from her speech before, like some utterances. And this is how KNNVC works. You start with the first frame in the source utterance, and you find the closest nearest neighbor in the frames from the target speech. So we took several utterances from Pune, and normally we use around 3 minutes of input utterances. We extracted features from them using a self-supervised model. We put those features in a bag and we shook it. Okay, so there's a bag of features here. For the source utterance, we pass that through our SSL model. We have LM layer 6. We get the sequence of frames. And then what we do is for the first frame, we find its nearest neighbors in this bag of features. Okay. If you want to be fancy, you can take the 4 nearest neighbors and average them. You then put that nearest neighbors there, that frame. Okay. Then you go to the second frame, you find its closest nearest neighbor, and you put that in the second position, and so on. Okay. And that is the end. That is actually the whole conversion model, not entirely. What you then do is you push this new sequence of features, you push that through a vocoder. This is a hi-fi GAN that's been trained to map WAV-LM features to a waveform, and that produces the output. Okay, so there's no model training involved. It's literally, we load in WAV-LM, we find nearest neighbors, we push it through a vocoder, and that's how voice conversion is accomplished. Okay, I'll stop there.
Maybe there's one question. It is voice conversion the same as voice cloning?
I will have to read the paper, but I think the papers, I think those terms are practically very used interchangeably. So it is, I will have to go and look at the precise definition, but I think they're very similar. So yeah, you're basically, but the point is you have a target speaker and you want new input speech to sound like that target speaker. So you want to clone this speaker's voice. I think voice cloning is sometimes used more generally. So maybe even in TTS, where the input would be text. I think people would also use voice cloning for that, like that term for the same thing.
I see. Maybe one question I have here is that if for the input of your vocoder, you only pass the green features or also the blue features to concatenate, or only the green features is passed?
Only the green features.
Okay.
So it's literally, I find the closest Pune features that I can get, and I pass that through the vocoder. The end.
Okay, interesting.
So the whole algorithm is like 4 lines, right? You load WAV-LM from Hugging Face. You do k-nearest neighbors using scikit-learn, or if you want to do it efficiently, PyTorch. You load a vocoder from Hugging Face, and the end.
Okay, interesting.
Yeah, so what we do in the paper is we compare to other voice conversion systems. Like I said, this was actually 2 years ago. So at that point, these were the state-of-the-art voice conversion systems. And you can see that their flow diagrams look a lot fancier than my flow diagram. This is our system diagram. Theirs have many moving parts. They normally train some model to explicitly convert. We have none of that. So we compared to these systems in the paper, and these are the results. I'll run through them relatively quickly. The important thing, of course, when you write a paper is you want your system, KNNVC, to have a bunch of bold numbers next to it, and that is what we accomplish with a very, very, very simple approach. So, but I'll just quickly talk through these metrics. So normally for voice conversion, you have 2 things that you care about. The output should contain the same content as the input. So if the speaker said a sentence, you want the output to also say that same sentence. And so we normally talk about intelligibility. Okay, so that sentence should be intelligible. And how you can evaluate that is you can evaluate it quantitatively by basically doing the conversion, then pushing the conversion through a speech recognition model and seeing if it transcribes the output correctly. And this is what's measured with this word error rate metric. So the lower the word error rate, the more intelligible the speech is. Basically, the closer the speech is to the original input's content. So intelligibility is one big thing. The other thing is you actually want the output to sound like the target speaker. Okay, so we fed it with my input. Herman said something. We want to make it sound like Pune. We actually want to evaluate that it sounds like Pune. So how we do that is quantitatively, we basically pass the output of the system through a speaker verification system. And then we evaluate how good is our system in fooling the speaker verification system. So we basically see, can the voice conversion system, can it basically fool the speaker verifier? So here, a higher error rate means that the speaker verification system makes more mistakes, which means we're closer to the target speaker's voice. Okay. And then these are subjective evaluations. So both of these are objective quantitative metrics. These two are subjective. So mean opinion score, you basically just play something to someone and you ask them rate on a scale from 1 to 5, how good does this sound? So this is very close to intelligibility as well. And then similarity is we play something and we ask how similar does this sound to the speaker that we want it to sound like, so to the target speaker. And you can see that KNN-VC does really well on both the objective and the subjective evaluations. You can actually use KNN-VC for a ton of different things. So I'll just play you some examples. The important thing is it relies on WAV-LM, and WAV-LM I've only seen English. But what I will play to you now is I'll play some input, and then I'll play the output, and then I will play the reference. I'll do it quickly again because my Mac viewer is wonky. So I'll play input, output, and then I will play what we wanted the output to sound like. So this is the input.
Anake hatte allen Körperschmuck, den ein japanisches Mädchen
The output.
sitzen.
Anake hatte allen Körperschmuck, den ein japanisches Mädchen sitzend
And then the reference, target speaker.
この前探った時は途中に反根の隆起があったので、ついそこが
Okay, so what this is the input is in German. The target speaker's kind of reference data is given in Japanese. It's a Japanese speaker. And then we're converting from the German input to the German output while having Japanese conditioning information. And WAV-LM have actually not seen German or Japanese, and it still works just with this nearest neighbor lookup. I'll skip this one because it's too awkward. I'll play the last one. It's a little bit weird. I will play the input, then I will play the target speaker, what we want it to sound like, and then I will play the output. So the input is this. Okay. We want it to sound like this.
The goat gave a leap, escaped from the soldiers, and with bowed head
Okay.
rushed upon the Bulu.
Then the output is this. Pretty weird. I know. But it's pretty interesting that, I mean, obviously WAV-LM has seen very few dog barks, but you can do interesting and wonderful things with it. Those are some fun examples. It's also been used subsequently in more kind of proper work. So the first 2 bullets here is from my own group, and the last 3 is from other people's work. So the first one here is I'll quickly run through this and then I'll take the question again. The first one here, this is a kind of an interesting case study. So we had a student here who had to give a final year talk, but the student had a speech impairment. They stutter quite a lot. And so what we did for the talk was the student actually wrote the script for the talk. Someone then read the script, and that would be the source. And then what we had is we had the student who stutters provide the reference here. So they read a part of Harry Potter while stuttering, okay? And then we used KNN-VC to, you have fluent source that you KNN match to the stuttered speech, and then you get fluent output that sounds like the student. So I'll just play you the output and then a part of the reference. So the output sounds like this.
Image captioning is the task of generating a short natural language phrase
Okay.
that describes relationships between
And
objects. Mr. Mrs. Closely of.
Okay, so you can, there's a lot of stuttering, and what happens is that KNN-VC only matches to the non-stuttered bits, and in that way it's able to produce fluent speech. The output sounds kind of a little bit bad prosody, but that's just because the source speaker wasn't great. It was actually me who wrote the script, but that's just why it sounds a little bit robotic. Okay, I'll do the one more example and then I'll take all the questions. The second example here is we have a project where we are building speech recognition systems for children. We're trying to do very early studies in literacy. And child speech is very difficult to come by because of ethical concerns. So what we did in this paper was I actually had some of my students basically read transcripts that were transcripts from child speech, so things that children said. And so this is adult student speech. And then what we do is we convert it so that it sounds like children using some child reference data. And then we use this as additional data for training our models. So I'll just play the Afrikaans example. So it was for Afrikaans and isiXhosa that we built these systems. So I'll play the input, the reference, and the output. And you will hear that the reference data is actually a British child, because we don't have the idea is that you can apply this even if you don't have child speech in the target language. So the input is this.
'n muis en 'n hondjie, die hondjie jaag vir die muis.
The reference,
Ticket inspector.
and then the output.
'n muis en 'n hondjie, die hondjie jaag vir die muis.
Okay, so you can hear it sounds quite like a child. I'll also just play the isiXhosa output. Okay, and that's an adult input. Other people have used KNNVC for a ton of different things. So singing voice conversion, applications in this R3 to healthy speech conversion, and very recently anonymization. Okay, I'll pause there.
Okay, so we have two questions. The first one is, does it scale well if training data is more? I believe KNN requires more memory.
Yeah, so that's a very good question. And it turns out that it plateaus pretty quickly. So in the paper, in the KNN paper, we actually evaluated with can't remember exactly, I think from 10 seconds to 8 minutes. And it seems that after 3 minutes, you don't get a massive boost. So around 3 minutes of reference data that's basically as good as it can get. I should say that many other voice conversion systems are focusing on much shorter segments. So I think KNNVC still works really well and is actually still at the moment very competitive if you have more data. But if you're in the 10-second range, it doesn't help that much. But for 3 minutes, you can load it in memory very quickly. The whole thing is extremely fast if you have 3 minutes of data that you're trying to match to.
Okay. The other question is, the audio quality is low. Is that the limitation of the vocoder?
I actually think the audio quality is pretty good, but that's maybe just me. I think some of these samples that I played, they sometimes sound quite scratchy. And that's mainly because the reference data is actually kind of low quality. So what we found is that if your reference, the data that you're matching to, is high quality, then it sounds really good. If the reference has background noise or things like that, then that would actually also come out in the output. And it's a question whether you want that or not. So sometimes, ideally you just want things to sound perfect, but there are cases where you actually want your conversion system to really accurately match the kind of the target that you're specifying. So later on, I'll play samples from other systems, which sometimes cleans up the noise. And yeah, so it's an interesting question. Do you want it to match the reference exactly, or do you actually want it to be cleaned up or not?
Final question maybe is it is about SSL model is known for capturing semantics, like phonemes, and not capturing pitch or timbre, which is something required for voice conversion. So they ask about, could you comment on how this model just works? And also the additional questions, the same person is about, do we need an additional vocoder to be trained, or you just frozen that one and just use a pre-trained one?
I'll answer the second question first. So we trained one vocoder who have LM to speech, and we trained it in-house on multiple speakers. So it's a kind of a universal vocoder. And then we freeze it. We never touch it again. This was a few years ago. It was really a pain to train. So I try and not retrain it ever. So my whole talk uses a single vocoder that's frozen. If we move to have LM layer 21 or whatever, then we will have to retrain it. But good question. The other question, which I really like, is said that, SSL features are known to capture semantics more than other things like pitch and so on. And I would say that our approach can only work if that statement is false. So basically what I'm saying is we very clearly show by doing these experiments that pitch is actually encoded still in the SSL features. And many other things, actually everything that you need to characterize a particular speaker is still captured inside these SSL features. They might not be, maybe probing experiments don't show it directly, but here we show that if you have a WAV-LM vocoder, then you can actually still find all of those things. And I think I'll comment on that because that really gets to the core actually of the talk, which is that we see stuff here that we don't necessarily see with probing experiments. And I would definitely say, actually, okay, yeah, this is the next slide. So because this is really, I think that was a great question because it reads exactly into this. What do we know about self-supervised representations from these experiments? It's difficult to know. I think we should be like a little bit amazed that this works at all. We should be surprised by that. And so what can we say for sure about self-supervised representations? And I think we can say two facts for certain. The one is that phonetic content is matched through cosine distance. And what I mean with that is when I take one of my SSL frames and I try to find the closest Pune SSL frame, those two frames will contain the same phonetic content, or at least enough similar phonetic content so that I can actually get intelligible speech out that matches the original content of the input. So that's fact one, and I think that's true. And the second fact is that speaker characteristics, including pitch, timbre, all of those things are still actually captured in the representations. Okay, if that was not true, then then this whole thing wouldn't work, and we wouldn't be able to synthesize from the green, the green vectors. We won't be able to get the target out. And it's interesting because these two things kind of almost seem to contradict each other. How can you, have both phonetically good matching, but then also speaker good matching? And KNN, the real trick that it uses is when I try to find the closest neighbor, I only look at the target speech. I don't look at my own speech anymore. I only look at the target speech. So I know that that frame will come from the target speaker. And if fact number two is true, then I will get intelligible output. But I will unpack this more like with the next approach. But let me quickly just show in kind of the latent space what I think is going on. So this is just a first attempt at understanding how this is working. So what I show here is actually UMAP embeddings in two dimensions of two speakers. There's a blue speaker and a green speaker. I hope the colors is okay for everyone. Hopefully my pointer helps if it's not. And I just took a ton of WAV-LM features from green speaker and WAV-LM features from blue speaker, and I visualized them in this two-dimensional space. And you can see there's actually quite a lot of structure that's shared between them. I could have colored this spice by phone. And what you would see then is that similar phones actually end up in similar locations in this two-dimensional space. So this, I can't remember exactly, but this could be R, and this could be the green R, and this could be U, and this could be the green U. This looks really nice. Full disclosure, just in terms of honesty, these are actually all silences. Okay, it seems there's different types of silences, which is true. I could have filtered this out, but it made the picture look cool, so I left them in. Okay, and blue silences and green silences end up close to one another. And what we're doing with KNN-VC is we're trying to find where you start with the blue features, and then you try and find the nearest neighbor in the green features. And it turns out that that works really well. It preserves content and then converts the speaker. So here is just where it ends up when you find the nearest neighbors. So I find the nearest neighbors in the high dimensional space, and then I project that down to the two-dimensional visualization again. And what you can see, okay, the silences are maybe the least interesting, but some of the other spaces like here, you've got some blue phones that end up on green phones, similar here. And there's actually a lot of structure here as well. You had that blue sequence and it ends up on the green sequence. In terms of silences, the same thing happens. So you have your blue silences ending on green silences. So this is the first attempt at kind of using this to see what's happening in SSL space. I will now talk about the second approach. So KNN-VC, great thing, used in several applications. And we thought, cool, we've mastered this advanced machine learning approach called nearest neighbors. Let's level up and go to an even more advanced machine learning approach called linear regression. And this is work that I did with Benji and then my two friends at Ubisoft, Marc-Andre and Julian. You can see that one of them have been in the field for longer because they know how to take really good headshot photos. Okay, so the linear VC is pretty simple as well. This is how it works. You get a source utterance that's in the source speaker. You encode that through your WAV-LM model. You get your sequence of SSL features. Then what you do is you take the first frame and you multiply that with a matrix, okay? And you get the green frame there. You take the second frame and you multiply it with that same matrix. So it's basically a linear projection of blue to green, okay? And you use the same projection. So multiply that one with a matrix, multiply that, project that in the same way, and you project all of the other frames in the same way. And the end. That's linear VC, okay? Again, you need a vocoder. Actually, I was really lazy, so I didn't retrain our vocoder. I used the same one that I used for KNN. And you get the output speech. And this is linear VC. So the big question is, of course, where does this single matrix that you use for all the frames, where does that come from? So it is a little bit more involved. I'll just step through it quickly. So what we do is we take some source speech. So that's like a bunch of utterances from me. We take some target speech, a bunch of utterances from Pune. We push them through the SSL model and we get frames out. And then we find nearest neighbors. So for each of the source frames, we find nearest neighbors in the target speech, basically do KNN VC. We then stack these frames in big matrices. So the source speaker gets stacked in a matrix X, and the matched target speech gets stacked in a matrix Y. And then we basically have a little multivariate linear regression problem where we try and take my features and project it to Pune's features by just using a matrix W. Okay. After doing this, so we do it on some source speech, some target speech. We actually use 2.7 minutes here, 2.7 minutes here, just for that speaker or that listener who asked that question. Then what happens is you get new input speech that you haven't seen before from the source speaker. And then what we do is we extract the sequence of WAV-LM frames. And each of these frames, we're just going to multiply with this W matrix. Okay, so each of the frames are just individually multiplied. And then we stick that through a vocoder. And that is the end. So slightly more involved than KNN. It looks like we're using KNN on the inside, which is true. But in the end, you get a single, you're just multiplying a matrix. So to that, the listener who asked the question about efficiency, now this is really nice. I don't need to do a nearest neighbor lookup at inference time. You do this matching thing once, okay? And then for all the speech that I want to convert, I just multiply it with this matrix that maps from source to target. Okay, so we wrote up this for interspeech, for this year's interspeech. So you can still come to my talk there if you're around. Turns out in the last few years, since KNN VC, voice conversion has advanced a little bit at least. So codec-based models have really taken off. So in this paper, we compared to an in-house version of SoundStorm, which is a codec-based language model where you basically use a little prompt from your target speaker that you append beforehand, and then you process the output. This is Julian really did the work on this to make it work really well. So again, we've got our little table. And here we compare to FreeVC, which is the best system from before, SoundStorm, the in-house one trained by Julian, and then KNN VC, which is kind of the inspiration for this approach, and then Linear VC, our new model. Intelligibility with word error rate. So this is objective measure. Speaker similarity with equal error rate, objective measure. And then our Ubisoft friends told us that we don't know how to do perceptual experiments. We should do it properly. So they didn't like what we did before. So they taught us about Mashra tests, where you basically, instead of giving someone, for instance, just one utterance and asking them, how good does it sound? You actually give them utterances from all the systems, and you ask them, basically jointly rank them, giving them scores out of 100. But you get a very nice head-to-head comparison. So naturalness evaluates how natural it sounds, like does it just sound good, the output? And then similarity asks, does it match the target speaker? That you don't want it to just sound good, you also want it to actually do conversion. Okay, now the frustrating thing about this table, and some of the reviewers also found this frustrating, is of course that linear VC doesn't have just bold numbers next to it. Okay, actually, yeah, it doesn't have bold numbers next to it. And I don't really care, because we're not trying to do state-of-the-art voice conversion. We're actually trying to use voice conversion to understand SSL features. But I think the point that you want to take away from this table is that actually linear VC does very similarly to some of these other approaches. So if you look at intelligibility, for instance, it actually outperforms KNN VC, which was its inspiration, and it gets close to Soundstorm. If you look at actually the naturalness scores, it does reasonably well compared to the other approaches. And then, sorry for the hooter, in terms of equal error rate, again, it does similar to the other systems. The best metric is actually similarity. If you look at how good does it match the target speaker, and you can see here that these subjective scores are actually, the variance is quite high. And so the difference between KNN VC and Soundstorm and linear VC is almost nothing. And Julian also did statistical significance tests, which shows that actually these three systems, in terms of similarity, is basically doing the same thing. Free VC actually sounds much better than the others, or yeah, quite a lot better, but it doesn't actually do really good voice conversion. Okay, so you can ask whether that's really useful. A side comment here that I should just make is, if you look at the similarity scores, you can see that for these three systems, they're actually basically lying on top of each other. But if you look at the speaker verification objective metric, you see that there's actually a big difference, 30, 33, 38. And this is just a little thing that we should take these objective metrics sometimes with a grain of salt, because a speaker verifier can maybe pick up on artifacts that a human listener can't pick up on. Okay. That was a long-winded way of saying these things are pretty much the same. Let me just play you some samples. So I'll play input, I'll play reference, and then I will play output from KNN VC, linear VC, and Soundstorm. So the input utterance.
In both these high mythical subjects, the surrounding nature, though suffering.
We want it to sound like this.
Then of a sudden, at midday, the sun shot out, hot and still. No breath of air stirred. The sky was like blue steel. The earth steamed.
Okay, now KNN VC output.
In both these high mythical subjects, the surrounding nature, though suffering, is still dignified. And in both these high mythical subjects, the surrounding nature, though.
Okay, I'll play the Soundstorm one. Now, the interesting thing about this is that there's actually a lot of noise in the reference. And actually, both of them, KNN VC and linear VC, kind of clears up the noise a little bit. Soundstorm does a much better job of clearing up the noise.
In both these high mythical subjects, the surrounding nature, though suffering, is still dignified and beautiful.
Okay, so point of the story is that actually KNN VC and linear VC, they sound very similar. Okay, let's just take a step back and ask, what is this telling us? So I think that there's a little bit of, we should appreciate how simple this approach is. Nearest neighbors, although I said it is a dumb technique, nearest neighbors can actually do highly non-linear things, right? It can, if you train a nearest neighbor classifier, it can put a very complex boundary around classes. A linear projection, it's literally like putting planes or lines in a space. And despite just doing a linear projection, we can actually get very good voice conversion output. And we should ask, like, what does this tell us about the self-supervised space? If I can just take my self-supervised space and multiply all the frames in that space with the same matrix and get a different speaker out, what does that tell us? Okay, so let's try and make sense of this. So the first thing I did was I used UMAP again. And here I've got the UMAP plot from KNN VC that I showed you before. And Here I've got the same UMAP plot, but now I apply linear VC. And the point that I want to make in this case is just that what we see here is, if you squint at this, linear VC is just doing something very similar to KNN VC. You can see this quite accurately with the silence mappings. It ends up in similar places, but even for other like proper phonetic units here and here, you can see that linear VC is basically doing the same thing as KNN VC. This should still surprise us. That just means that the nearest neighbor thing is actually doing something linear in this space. Okay. So the next thing we did was to try and kind of unravel how is this working, is we actually visualized those projection matrices, the W's, and we've visualized a few different W's to see what's going on. So what I show here in this, we can just focus on this plot, is each W is 1024 by 1024, but I just show you 256 by 256, basically the first rows and columns. And what I did to visualize the matrix was I took the values, I took the absolute value of the matrix, and then I applied a threshold and just binarized things so that everything below the threshold goes to 0 and everything above the threshold goes to 1. And then I just look at the matrix. And this is actually what we see. Now, this on its own is actually a little bit surprising. You should because there's no reason that there should be structure in this matrix. But what we see is that, for example, dimension 35, there's this kind of line running down here. Dimension 148, this line running down here, and similarly. Now, what that says is that these particular dimensions are actually used in predicting all of the output dimensions. So there's kind of structure in this matrix, and these dimensions seems to be particularly important. What we then did was we basically wanted to see, well, how does this structure transfer to different settings? So here I was converting to speaker 1272 to speaker 1462. Now what I'm going to do is same thing, but I use different 2.7 minute subsets from this speaker to this speaker. Okay, so it's the same speaker, but using different subsets of speech to learn that W matrix. And again, those same dimensions kind of light up. Then we swapped speakers. So going from speaker 1272 to 1673, again, those same dimensions seem to be important. And then 8842, so two completely different speakers. And so what this tells us, difficult to interpret this, but it does say that there's some structure in the matrices, in the projection, some common structure that's in a way shared by all the different types of transformations that you can do between any pair of speakers. Okay. Now, this is a little recap from, I don't know, we did this in second year engineering mathematics. What does it mean to multiply a vector with a matrix? Because that's essentially what linear VC is doing. What can happen with that vector if you do that? So if you constrain the matrix, the W matrix in a particular way, then when you multiply a vector with a matrix, if you constrain it in this particular way, then it's just rotating the matrix in the vector in this high dimensional space. When you have a slightly more complicated matrix, then what you can get is you can get shearing, which basically means stretching out in a specific direction. And I can stretch out in a different direction as well. So these are all in 2 dimensions, but these things can generalize to higher dimensions as well. And in general, if you just have a general W matrix, what you get is you can get rotation, you can get shearing, which is stretching out in a specific direction, and then you can also get scaling, where you basically scale the whole monstrosity in or out. You can also get flipping. So I don't mention this on the slide, but you can basically take the mirror around an axis. And in general, that's what happens when you multiply a vector with a matrix. Okay, and what I'm going to do now, after taking the question, is I'm actually going to see, can we think about these different operations that a matrix multiplication can do? Can we constrain them in some way and then learn something about the SSL space? But I'll first take the question.
Yeah, maybe we could have all the question at the end, so we could go over all the talks, and then we have the question. Maybe it is easier.
Okay, perfect. Okay, cool. Then I can rant on. Okay. Okay, cool. So just to recap, matrix multiplication, rotation, shearing, scaling, flipping. Okay. You can also have a bias, but I will try and ignore the bias except for one slide. Okay, which is this slide. So what I'm going to do now is linear VC has this very nice thing that we can actually constrain the matrix in a way and then see what happens when we try to do voice conversion, but constrain the types of transformations that are allowed. So the first thing is the most stupid transformation that you can think of, which is to just use a bias vector. And so how this works, I need to explain these little, do you get Cheetos in Canada? Anyway, I'll explain this little Cheeto diagram. So here, this is features from one speaker. So this is Herman's features. This is Pune's features. And in this approach, what we're going to do is we're basically going to take some features from me, some features from her, calculate just the average distance between the two, okay? Then I'm going to take some of my input speech, and I'm just going to add a vector, the same vector, to all of the frames, and then push that through the vocoder, okay? This is really stupid, but cool, let's see what happens. So I'll play input, I'll play the target speaker, and then I will play the output. The input is this.
In those very early times, there was a man
Target
named
data.
Deucalion.
And while taking the rope off, he shook himself and seemed to
Okay,
say,
the output.
In those very early times, there was a man.
Okay, I'll just play the input and the output again.
In those very early times, there was a man.
In those very early times.
Okay, so the output doesn't sound like the target speaker exactly, but it did move. There's some change that happened in the speech. So the voice characteristics changed. This should, like, it's a little bit crazy. So you take a sequence of vectors, then I add some vector to them and I push them through the vocoder, and that doesn't completely screw things up, okay? And it is doing some conversion. For the rest of the talk, I won't talk about the bias vector again, but I thought this was kind of cool. Okay, let's actually constrain that matrix. So what I'm going to do now is I'm going to say, cool, you're going to multiply each of the frames with this projection matrix W, but you're not allowed to shear and scale. You're only allowed to rotate. Okay, so basically you're only allowed to take my little Cheeto and you're only allowed to rotate it. And that's the only thing that's allowed. Okay, you can also reflect. So rotate and reflect, but you're not allowed to stretch it out or shear it. When this happens, the matrix is an orthogonal matrix that you get out, that W. So I'll play input, reference, and then I'll just play the orthogonal projection.
In those very early times, there was a man.
and while taking the rope off, he shook himself and seemed to say, you think that
In those very early times, there was a man named Deucalion.
Okay, and then I'll play, it's getting pretty close to the target speaker. Then I'll just play the full linear VC. So that's when you allow shearing and scaling as well.
In those very early times, there was a man named Deucalion.
Just orthogonal.
In those very early times, there was a man named.
Okay, they're pretty similar. This one has a little bit more. It sounds more like the target speaker than this one, but they're getting pretty close. And what this shows is that actually, to a high degree, you can, by just rotating and maybe flipping the space, you can actually get close to the target speaker's voice. So you take your SSL features, rotate, the end, okay? It's not perfect. It's not perfect voice conversion, but you're getting close to the speaker that you want. Okay, so how do we make sense of this? What does this actually tell us if we're trying to visualize what's happening with the geometry of the SSL space? And what I should emphasize here is I'm going to show you a sequence of basically little, it's not real data, it's generated data of how I think that the space is structured. So it's going to be little cartoon diagrams. I will show you how I project from one speaker to another, and that projection is real. I use the same code as we used for KNN VC or for linear VC. And this is basically my view of what I think is happening in the SSL space and in the geometry. And I think my view is supported by the results that we achieved. So this is just my first little picture. This is how I think the SSL space is structured. Okay, there's two speakers. Okay, and represented by the two little S's. The one speaker, let me just see if I can move this forward and backward. I don't think I can. I'll just go again. the one speaker is this one S, and the other speaker is this other S. Okay. They live in different spaces or different planes within the SSL space. So SSL features are represented in 3 dimensions now. But importantly, what's happening is that there's some common structure, okay, in their respective spaces. And what happens when we do something, okay, so what I should say is the colors here are kind of like, you can think of them as these are, I don't know, specific vowel. That's ah, okay? And here on this speaker's S, that's also ah, okay? And this is maybe, and this is, okay, but they live in different regions within the SSL space. If we do something like KNNVC, then what we're going to do is we're going to start with a particular speaker and we're going to say, in the other space or in the other plane, what is the closest feature? Okay. And what happens when you do that, it's represented with the little lines here, is that you end up, you get these lines, and my k still ends up as a k from the other speaker, and similarly here. Okay. And then when you synthesize out from this, then you get back the original, the target speaker that you want. Okay. Now, what happens with something like linear VC, and the next animation that I will play is the orthogonal one, where you're just allowed to rotate. What linear VC tries to do is it tries to rotate, okay, it tries to rotate the one space onto the other space, and then it can shear and stretch as well. Okay, but I'll first just show the one that just allows for rotation. So the one that allows just for rotation, you kind of have this happening. And then things are moving closer. It's not perfect. But the 2 planes gets kind of aligned. And then finally, this is the one with the full matrix where you have both shearing, scaling, and rotation with the one space mapping on top of the other one. And I think that's kind of what's happening. Okay. That's kind of the end, except that if this is true, if my claim is true that you have like this common structure between the 2 speakers or multiple speakers, and the phonetic content is structured in a similar way, but they lie differently in the space. If this is true, then we should actually be able to, in some way, factorize out the common space or a common space. And with that, I mean, in this little toy example, figure out that there's an S shape that's common between the 2 speakers. And then we should be able to basically go from that S shape to either of the speakers that we want. And so this is the last part of the linear VC paper. It's a little bit more involved, but hopefully I can explain it somewhat clearly. And this is an approach that Benji came up with. So the idea here is that if you have a common space that's shared between speakers, then we should be able to factorize it out. And so he came up with this content factorization approach. I'll just step through this. So what you do is you have features from capital K different speakers, okay? So speaker 1, speaker 2, speaker 3. I won't go into all the details, but basically what you do is you make sure that the content is the same across all these speakers, okay? So they're all saying the same thing, but I've got some Herman features, I've got some Pune features, I've got some Mirko features, okay? And each of us have our own little matrix here with our features in it, okay? Then what we will have is we will have a common space that's shared between the 3 of us, for instance. That common space is called C, that's the common content. And then for each of us, we will have a unique speaker transformation matrix that goes from this common content space to the individual speakers. So there will be a Herman S matrix, a Pune S matrix, a Mirko S matrix, okay? And what we're going to try and do is we're going to try and learn these C and S matrices so that we can approximate our individual features by using a common content space and then individual speaker matrices. Okay, I'll just show this. So the idea is really that this content space should be a low dimensional space, should be lower than the features. And what we're going to do is we're actually going to constrain the rank of the multiplication here so that it's less than or equal to R. And what that basically means is that we're trying to approximate, for instance, my speech by having common content common content matrix multiplied with my unique speaker matrix. And this common content space will have a lower dimensionality than my original features, and that we can impose. And you can actually solve this, this problem using SVD, so singular value decomposition. You can solve this optimization problem. Okay, I hope that makes kind of sense. If this works, what you can then do is you can actually use this approach for voice conversion. So what that would mean is you learn, for all your speakers, you learn their S matrices. And then what you do is you get new input from some speaker, from one of the speakers that you've seen. What you then do for that new input is you figure out what the content is for that new input, and you use the pseudo inverse to do that, okay, from your input speaker. And then what you do is for your target speaker, you then just take the new content and you multiply that with the target speaker's matrix. It's a little bit involved. You can read the paper, but I hope that makes sense. So basically you get new input, you project into the content space, get the content, and then you convert to the target speaker by just multiplying that content with the target speaker's matrix. Okay. Does this work? Yes, it actually works pretty well. The cool thing is we also get a little handle that we can wiggle. The handle that we can wiggle, yes. The R, the rank here, which we can change. And depending on how you change it, the properties of the transformation can change. So it turns out, let me quickly just explain these plots. So here we've changed R. We've basically varied R through this content factorization approach. And then in this plot, we look at how intelligible the speech is as we vary the rank. And then here we check the speaker similarity to the target speaker. So we're going to do voice conversion. And there's a few like pretty surprising things here. It seems that you can actually get intelligible speech with just a content matrix with a dimensionality of 6. You can get intelligible speech. It doesn't match the target speaker really well. But then as you increase the rank, you can actually start to match the target speaker pretty well. You can actually get even more intelligible speech at some point. So for our voice conversion experiments, we ended up using a rank of 100 in our perceptual experiments, because that gives a pretty good trade-off. We match the target speaker quite well, and we get very intelligible speech. So I'll quickly play you. You've heard the source, you've heard the reference before. So with a rank of 100, it sounds like this.
In those very early times, there was a man named Deucalion, and he was the son of Prometheus.
Okay, so full linear VC without any constraints sounds like this.
In those very early times, there was a man named...
Okay, so this one is with 1 to 4-dimensional features. This one was with 100-dimensional features. When you go, I'll just play this in sequence, 6, 16, 100, 256. But I'll just say quickly what happens when the dimensionality is too low, then you actually really struggle to match the target speaker. Intelligibility also suffers. As you go up, that improves. At some point, you're actually adding too much information from the source speaker. So then the content matrix actually there's some leakage from the source speaker that goes in. So I'll just play this in sequence. So this is for a rank of 6. So I should just emphasize, this is 6-dimensional features that we just effectively synthesizing from.
In those very early times, there was a man named Deucalion.
Okay, 16.
In those very early times, there was a man named Deucalion.
Okay, 100.
He was the son. In those very early times, there was a man named Deucalion.
Okay.
And he was the son of Prometheus.
And 256, this is where there's some source leakage. Sorry, I don't know if you can hear the hadidas. It's like South African birds above me, but that's fine.
In those very early times, there was a man named Deucalion, and he was the son of Prometheus.
Okay, so this one gets pretty confused. Okay, so in the paper, this is the same table that I showed before, just with the content factorization added. And what we see is that this content factorization approach with a rank of 100 actually gives pretty similar voice conversion results to linear VC, despite just working on 100-dimensional features. What I will show now is just my little animation, but with the content factorization space. So I will show the one S, I will show from one speaker, I will show the S from the other speaker. And then what I did was just in green on the animation, I plotted the C matrix. So the actual content space. And it ends up looking like this. So I should emphasize the C matrix, which is in green here. It's not in the same space as the SSL features. I just plotted it at basically at 0. And so what you can see here is that, well, how you should think about this is that from the one speaker, you can map to the green space by just basically doing the speaker specific transformation with the little S1, or S2, or S3, like the Herman S or the Puni S. And you can go from any speaker to this S space, and then you can go back out from that specific S to the target speaker by just doing the S transformation again. And this little, I mean, it's toy data, but it uses exactly the same lines of code that we actually use in our paper. So I think it's quite convincing that this is actually what's going on. Okay, I will conclude. I'm almost at the end. What I want you to take away from the talk is that simple approaches are still very useful. We need to teach students about linear regression and about nearest neighbors, despite ChatGPT taking over the world. You can actually do practical stuff with it, like by just carefully using simple approaches. We've been able to do state-of-the-art voice conversion. I've kind of not spoken about this in great detail, but probing experiments where you train, for instance, linear classifiers on features to see what those features contain. I think those are useful. They have their place. But at the same time, I think something like synthesis or voice conversion or voice manipulation experiments like these can provide a unique perspective on the SSL geometry. It can allow us to have hypotheses and to manipulate the space and actually see if those hypotheses hold. I think synthesis allows us to just very quickly see what the salient effects are. I mean, actually hear what the salient effects are by just manipulating the space. In our group, what we're really looking into in future work is to formalize my little cartoon animations. I'm pretty sure that's what's happening, but you can actually construct hypotheses and construct proper experiments to test whether what I'm saying about rotations and so on is actually true. And I think it's not easy, but we could formalize some of those hypotheses and not just have cartoon animations. And then I think another big thing that we're quite keen to do is actually use the content space in downstream speech applications. So I've mentioned I work on zero resource speech processing a lot, where we try and basically just see what we can learn from a collection of speech audio without any labels. And in that space, we often use techniques like dynamic time warping, where we're trying to align things to, for example, cluster words into groups. That often becomes computationally quite tricky if you're working with 1 or 2 4-dimensional features. And if you can do that on just 16 or 6-dimensional features, I think there's a lot of computational efficiency that we can gain from that. This is my second to last slide. So this is actually the slide that I normally start my talks with. So in my group, my kind of grand vision is that I want to build speech systems that learns with as little supervision as possible. And that has applications for speech technology, but it also has applications in trying to figure out how human infants learn, basically cognitive science, and trying to unravel how small children acquire language through this kind of amazing process. And I'm quite excited to see how some of the intuitions that we've gained by doing voice conversion, which isn't on this picture at all, how that can help us inform and look at specific things in these self-supervised models, which maybe coincides with the way that infants learn language. And there are other groups looking at that. I think that's quite interesting, looking at perceptual learning and so on. And hopefully we can kind of glue these things together. It's important to say, like models like WAV-LM and Hubert, they're trained completely without labels. Just like a small child becomes a pretty good speech recognizer without seeing any text. Hubert and WAV-LM is probably trained on more speech data than a 4-year-old sees, but I think a lot of the insights that we gain there can actually transfer as well. This is the final slide. So if you want to do KNN-VC, Benji has a very nice repo that he and Matthew put together. It's just a few lines of Python and you can do KNN-VC. I made the linear VC kind of repo, so it's not as nice, and I should still patch it up a little bit. But if you want to play around with it, definitely go and just find the code, clone it, and use these things. I also have more samples on the little sample webpage. The end. Okay, now I can take questions.
Thank you. Thank you. It's a very nice talk. So maybe we have time for few questions. I would like to start myself. So you use layer 6 of VaVLM. Is there any reason for choosing that specific layer, or any heuristic? Like, why not using multiple layers or different layer?
Yeah. So I think the honest, okay, there's a scientific answer, which is someone like Ankita Pasat, who works in Karen Levishku's group, and other people as well, but her papers are particularly nice to read. She did a ton of analyses on different self-supervised models to see what's happening at different layers. And I think I can't recall exactly the exact layer, but a lot of our decisions are actually based on her papers, where we just basically pick those specific layers. We do play around with the layers a little bit to just make sure that it works. I know Matthew and Benji, for instance, what they did at some point was to try and do the KNN matching with one layer, which would hopefully be like more phonetic, and then use a different layer, which is more speaker specific, to do the synthesis, because nothing stops you from doing that. In the end, with a lot of experimentation, they found out that just like using layer 6 for both, it actually works pretty well. And then when I got to linear VC, I was too lazy to retrain the vocoder, so I just stuck with layer 6. I did retrain one vocoder. I can't remember, that took like 2 weeks, because I'm not the best coder. I can't remember exactly what I think I trained that actually on mHubert, which is a multilingual version.
Nice.
Yeah.
Okay, makes sense. So a question from audience in the chat is, could you please mention what equal error rate and naturalness measure? In what cases would I rate an audio as more natural and vice versa?
Yeah. Sorry, maybe I shouldn't. Oh, that was quick. I should actually, I don't know if Julian is on this call, but I will explain it, and then if I'm wrong, then I'm wrong, not Julian. But so the naturalness, these so basically what happens here is a listener, a human, gets shown several examples in like next to each other, and for naturalness they just get shown the example and they need to listen to it, okay, and they're just asked with a very carefully designed description, please rank how natural does this sound, like does it contain artifacts, like basically is it a good synthesis that comes out. They don't know what the input is and they don't know what the output is. Normally, you also give them like an upper bound and a lower bound. So the upper bound could be natural speech and the lower bound can be distorted speech, for instance. And you want to make sure that the raters rate the distorted speech as pretty low. So that's naturalness. So it's actually people sitting with headphones. And in this case, we actually handpicked our evaluators. In the previous one, we used crowdsourcing, but here it was people that has background in, basically grad students with background in speech. They didn't know what we were testing, but they would listen to things. Similarity, sorry, I'm fudging over the details because honestly, I can't remember everything. It's in the paper, so you can go and look at it carefully. So that's a Mashra test. It's basically when you rank several systems at the same time, and you can yank the bars up and down for the different systems. You listen to all of them, and then you say, oh, this one is slightly better, so I'll make that a little bit higher out of 100, and so on. Similarity, you're actually told this is what the thing should sound like. So this is an example from the target speaker. And then you're presented with different utterances from the different synthesis systems and asked which ones of these matches the target speaker the best, and again rank it out of 100. And Julian carefully designed the little prompt. We actually went through a few iterations where we changed it to make sure that similarity, it very clearly, so if there's voice artifacts, for instance, that should be ignored, and it should just be like, does this match does it sound like the target speaker, even if it's like sounding like the target speaker over a telephone? That should be fine. I hope I answered that well. The objective stuff It's a little bit intricate, but you can, like I would just encourage you to read the paper, or actually the paper that this paper cites to explain this, this metric.
So while we are here, maybe a follow-up question is that, does the vocoder play a part in naturalness and audio artifact? Like, would a better vocoder give a higher score or not?
Yes, a better vocoder would give you a higher score. In the KNNVC paper, they actually trained 2 vocoders. The one, they basically do a little bit of data augmentation so that the vocoder sees input that looks like it's been matched already. And they have these very nice curves that show that you get a small boost by just training the vocoder carefully. I think it should be clear from my presentation that I'm lazy, and so I didn't want to retrain the vocoder, but I'm pretty sure, I don't know if you want to write a paper about this, but just training a more fancy vocoder would definitely boost the performance.
Okay, and maybe the final question is that, given the linear nature of linear VC, does that imply that VAVLM features are somehow disentangled in the latent space? If yes, I would imagine that a few features from a 1024 dimensional space are related to important feature to voice conversion, but not all. Based on your experience, is W a sparse matrix or not?
Okay, cool. That's an excellent question, which makes me I hope it was asked in minute 15 and not at the end. Maybe it was asked at the end, because I guess that's kind of, I didn't say, the question actually put it maybe better than I did in the talk, but this is exactly what this is trying to show. Yes, you're absolutely right. The magic of all of this happens with WAV-LM, and without it being told or explicitly encouraged, there's linear disentanglement that happens in that specific layer. And yes, you're completely right. Specific directions, as subs, it's a little bit difficult to talk about like dimensions and so on, but let's just do it in a hand wavy way. You're absolutely right that there's a handful of dimensions in this high dimensional space, or maybe I should say a handful of directions in this high dimensional space that characterize a speaker. And that is exactly why we're able to do this. And even like the little, maybe I shouldn't go back to this, but even this, like, shouldn't try and do this. I hate it when my students do this, but even these pictures actually show this very concretely, that there's like a handful of dimensions that are common or important to all of the transformations between different speakers. And these dimensions essentially are maybe the dimensions that are important for characterizing speakers. And that's exactly what we're doing now. We're actually trying to see what are the directions in the SSL space that characterizes speakers. I should say that now I can't remember Ollie's surname, but Ollie, a student of Sharon Goldwater, has done a really good paper on this. Also with Hao Tang, I think, on that paper that talks about exactly like the orthogonality of that there's orthogonal directions in SSL feature space that's orthogonal to content. And she actually quantifies that using like probing like experiments and using PCA actually as the visualization tool. And she shows quantitatively exactly what you're saying, that there's speaker directions and that there's content directions. And we kind of, what linear VC is doing is exploiting exactly that that structure that's happening.
Okay, perfect. I think we're done with all the questions. Thanks a lot for the great talk, and thank you for accepting our invitation. Thank you everyone for joining. Next week, we have Andros Chandra from Fair Team at Meta talking about Meta Audio Box Unified Automatic Quality Assessment for Speech, Music, and Sound. Looking forward to meeting you all next week. Thank you.
Thanks so much.